Welcome to this lesson. So in this lesson today, we'll be discussing chapter 4 of my book, Multi-Agent Orchestration Pattern for Enterprise Scale System. So in chapter 4, we have task allocation and resource management. So task allocation in multi-agent system is very, very important as well when you are designing multi-agent system for an enterprise. It is very, very important that you determine the source of the task, how the task should be allocated, whether they are specialized agents that can handle the task. You should also be able to determine the time of completion of the task and whether the task has been completed or not. So of course we have 8 sections as usual, where we in all the 8 sections we discuss how tasks can be allocated, how it can be decomposed, how you can dynamically assign tasks, how you can load balance tasks between agents, how you can manage resources by implementing resource pooling and sharing mechanism, and how you can resolve conflicts between agents using policy and compliance, and how you can implement capacity planning for agentic system. And then in 4.8 we consider performance optimization, where we discuss metric collection and the kind of metric that you should collect when you are implementing task allocation and resource management in multi-agent system design. So this is moving from theoretical agent capability to consistent enterprise performance and service level compliance. So task allocation is very, very important in multi-agent design. The task allocation decide which agent should handle which work. Okay, it allows tasks to be assigned to specialized agents, and it also allows tasks to be broken down based on rules. So when you are designing for or breaking down of task, which we discuss in section 4.1, you can implement the following rules for efficiency, because efficiency is won or lost in how work is broken down before the first agent is even assigned. So we have the first one, which is called the golden rule. A task should be completable without needing to coordinate mid-execution. So a task should be designed to be completable without needing any external execution or any specialized workflow outside the agentic system design. So when you are breaking down a task, make sure it is structured and completable. Number 2, context as a fuel. So we can break down tasks based on task context. We are going to see the architecture at the end, where we define the input request, or where the task should come from, and the business use cases. So context, questions should be upstream task with answer provided as context. So this here, what we mean by that is that if you break a task down into like 5 tasks, task 1 can complete independently, then task 2 should request answer from task 1 before beginning operation. So thereby you implement for completion of task, and then the next agent to implement task 2 gets context or answer on what is going on from the agent that implemented task 1. Then we have 3, explicit depths. So relationship must be declared upfront, not discovered at runtime. So make sure the relationship between agents is determined when you are breaking down the task, not after the task has been assigned. So when a task is being broken down, the specialist agent that will handle the task must also be identified and put into consideration and be linked together based on the task decomposition. Then we have rule 4, parallelization. So parallel execution can reduce a 15-minute process to the lowest task, which is 8 minutes. So tasks can implement in parallel. That is, tasks can be taken together. If they do not depend on each other, they can be implemented, the implementation can be parallel, where you have completion of task flow uh, at a lesser time. Okay, so we have a task decomposition. We are still in section 4.1. So task decomposition involves breaking down larger business workflow into smaller tasks. This makes tasks to be independent. It makes tasks to be parallelized or parallelizable, as we have discussed in task rule. It also makes tasks to be assignable to one agent or a specialist agent, and it enables tasks to be monitored, and it enables easy combination of tasks and easy completion of tasks. So defining the task model. So task model is very, very important. You must determine the pattern that the task the pattern that the task will be followed until it is completed. So a standardized data structure for managing dependency, priorities, and context across the agent network. So it is very, very important that you define task model. And then we have three model in this part. We have dependency tracking, where you use depends on, where you build tasks based on dependency, just like when you are designing a data engineering pipeline, one task depend on each other. So task 2 should depend on task 1, task 3 should depend on task 2, and then you have sequential execution of task, which also improves completion. You can trace the path, you can monitor which task failed and why it failed. Then we have priority classes ranging from critical outage sanction to background nightly maintenance. So critical tasks can be taken first before the less critical one can be considered. So that is priority. So prioritize tasks based on their importance or requirements. Then we have capability routing. So ensure tasks are only feasible to agents with matching specialized skills. So when you are designing for task decomposition, do not design do not design a confusion into the system by allowing agents the capability to be able to take on any task. No, let tasks be routed to specialized agents. Let each agent have their capability and let them know the tasks that they can handle and the one that they cannot handle. So implementing functional decomposition. So how do you design for the composition of tasks based on functional requirements of the problem? So mapping distinct business capability into independent parallelizable units. So this flow will help, for example, when you are designing a procurement or supply chain multi-agent system, you can follow this pattern. So task 1 can be vendor analysis, which start immediately because it is the first task and it is independent on any task. Okay, so when it is completed, as task 1 is, ongoing, task 2 can begin in parallel and run in parallel to maximize throughput because it does not also depend on task 1. Then financial review depend on the completion of task 1 and 2, and it is triggered after the vendor data is available from task 1 and task 2. Then after that, legal review can begin immediately after financial review, and then conditional steps should be executed here, where you have higher risk task being passed to legal review or passed to human in the loop. And then we have ERP entry. So this is where the task or the completion of the task is passed on to the database for final step for analysis and visualization and review of results. So this is how you can design for functional decomposition of task. Then we have dynamic task assignment algorithms. This is what we discussed in section 4.2. So system must decide which agent should handle what task. And system must also know when should the task be assigned and to which agent the task should be assigned. And what if the best agent is overloaded? And what if an agent fails? So all this design pattern must be put into consideration. And to implement this, we have what we call how to handle uncertain or goal decomposition. So this is discussed fully in section 4.2, where we discuss trigger-based logic. So which is a critical classification spans war room and stakeholder notification task. So tasks can be implemented based on trigger, and it can be implemented metaphorically, like a doctor ordering test based on initial consultation result. And then you can have adaptive safety, where you have if compliance finds action match, the system inject legal hold and vendor suspension. So these are, ways that you can handle uncertainty in goal decomposition by following trigger-based logic, by implementing adaptive safety, and so on and so forth. All right, we have section 4.3 where we discuss load balancing across agent network. So tasks should be load balanced based on capability, based on the capability of the agent, the current load of the agent, the health of the agent, the task duration, and the quality of task outcome. So agent load balancing uses threshold. So you should know when agent is healthy and when it is not healthy. You also know when agent is overloaded. So this pattern can be followed using global feasibility to find the optimal match between pending work and available expertise. So we can implement global feasibility, which prioritizes global optimization above local optimization at the cost of global system health. And then we can use multi-factor scoring, which balances immediate availability against historical success rate and deep specialization. We also have priority queuing. This ensures high urgency tasks take the next available agent regardless of arrival order. So this is what we discussed fully in chapter 4. And then we in chapter 4, section 4.3. And then we have section 4.4 where we talked about resource pooling and storage sharing mechanism, how resource should be pulled from the system and how it should be shared. So here you can implement town-bound resource leasing. Okay, so agent compute for shared resources such as LLM API, rate rate limits, database connection, ERP sessions, license legal research sessions, regulatory data field quotas, external API limits. So all this, of course, agent will compute for them. So we can implement time-bound resource leasing in this kind of design. So this prevents system deadlock, rate limit, exhaustion, fire time to leaves. So you can design maybe 200 task, 200 requests per minute, where agent request capacity is limited to 200 per minute. So we can have 10 seats where you have concurrent section available. So you can have 10 concurrent task or 10 concurrent resource requests at a time. So this disallow the system from being overloaded with requests. So we have a priority-based scheduling, which is what we discussed in section 4.5. So priority-based scheduling ensure urgent work is handled first. Okay, so priority queue can staff low priority task. Scheduling must balance business urgency with fairness. So here you can implement scheduling here, and then priority task can be handled before let's prioritize one, and the urgent work can be handled before less urgent one. So this ensures that high business value work is prioritized without permanently blocking background tasks. And then we can see the operational priority logic in this chart, where you have critical task being implemented first, then as critical task is being implemented, background task can continue in that pattern. So, and then in section 4.6, we talked about conflict resolution and negotiation protocols. So conflict should be resolved based on policy and compliance that has been integrated into the system. So policy-driven conflict resolution and handoffs should be a standard design pattern in multi-agent system for the enterprise. So defining business-centric rules for resource disputes and specialist escalation before they happen. Of course, we know that priority always wins. Deadline nearest is very, very important, which regulates resource which regulate filing proximity, and it ensures that filing proximity takes precedence. You can also implement first come, so where the first task is implemented before the next one that follows, which allow order and task churn. And then we have a specialist handoff, agent transfer to specialist. So not all agents are specialized to resolve a particular task. So specialist agents can be assigned specialized task, which allow also completion of tasks without any failure. Then we have human review. So escalate tasks to human review when it is beyond the agent's capability. So these are ways that conflict can be resolved between a multi-agent system. So conflicts must be handled by defined policy, not ad hoc decision or assumption. Then we have section 4.7, where we discuss capacity planning for agent or system. So in capacity planning, use pattern workload. Okay, always make sure that you use pattern workflow when you are designing for capacity planning. But we can study more on this in section 4.7, and in section 4.8, which is the final section, we discuss performance optimization techniques. So performance optimization, or you can implement catching and batching. Catching is when the immediate or task or operation in the system are being catched using a catch database like Redis catch, and tasks can also be implemented in batching, where we batch tasks into groups, and when one group is done, the other group begins. So this reduces operational costs and latency by eliminating redundant computation and setup overload. So here we have measure then optimize. So to optimize multi-agent performance, you measure then you optimize, because you cannot optimize what you don't measure. If you are just monitoring without taking measurement, how will you optimize the system? How will you know when the task is completed or when it has failed? How will you know when an agent is healthy or when it is overloaded? So measurement is very, very important if you want to achieve performance optimization. So these are things that can be measured in task allocation design for agentic system. You can measure LLM inference calls. You can measure LLM API calls. You can measure database query. You can measure license resource limits. You can measure queue backlogs. You can also measure slow specialist agents, okay, so that you know when an agent is healthy and when it has failed. So, and then you can use catching and task batching to also enable performance of agentic system operation when they are handling a task based on schedule or in parallel. So these are ways that we can use catching and batching. The first one talked about catching. So content address catching. They are based on task type, payload, ensuring identical input yield catch resource instantly. And then we have task batching. This is grouping 50 school reorder evaluation into a single LLM call and can reduce API cost by 50 times and processing time by also 50 times. So task batching, of course, can is very important, especially when you have a heavy task or task dependencies that is very complex. So you can batch them just like we have batch and a real-time processing in data engineering workflow. And then we can have throughput and latency. Batching is ideal for background supply chain tasks, but inappropriate for user-facing legal reviews where humans are waiting. So this is also very important to be thing to put into consideration when you should prioritize throughput over latency. So uh good background, so this is good for background, high volume work where throughput matters more than latency. So this is this pattern three, throughput versus latency. So that is task batching. So throughput is better when you are implementing task batching, and then for content address catching, you can implement is good for when latency is required. So performance monitoring, as we have said earlier, you cannot optimize what you cannot measure, okay? Because measurement is very important. Observability is very important when you want to uh, check the performance of the system that you have designed. So, and these are kind of metric that you can design for a multi-agent system. Number one, you can measure queue depth over time. Number two, you can measure task duration by type and agent. Number three, you can measure error rate by agent. And then we have number four, you can, yeah, there are just three of them. So when you collect this metric then and determine the following, then you can know whether an agent is overloaded or unhealthy, and then you can resolve and debug, and then the system will operate uh, seamlessly. So optimization should be based on measured bottleneck, not assumptions. And the production operation, this allow performance optimization in production operation of multi-agent system design in the enterprise. And then lastly, we have everything put together into this single architecture. So this is the single architecture that describes everything that we discussed in chapter 4, task allocation and resource management, routing the right work to the right agent. So in stage 1 here, this is where you determine the request intake. So where does the task come from? And so this is taken from workflow, from business unit, and from task context. And this is fed into task decomposition. So when the intake is known, then the task can be collected and decomposed and broken down into smaller subtasks, which allow for structured operation and implementation. Then this is passed on to stage 3, where we have decision layer. So this is where you design capability registry, policy engine is applied, and priority rules. Tasks are assigned based on priority, and agent can implement this, agent can use this decision layer to determine which task they can take on and which one they cannot take on. Then we have stage 4, scheduling and queuing. So here we define task scheduler, priority queue, and load balancing. So this load balancing will allow you to determine agent health, whether it has failed or whether it is being overloaded. And then we have stage 5, which is execution pulls. So this is where compliance pull from LLM budget, analysis pull from tool quotas, review pull from database, and then automation pulls from human review capacity for tasks that are above agentic capability. And this is fed directly into stage 6, where we have a resolution. So this is where the system determines whether a task has been completed, whether there is conflict of resolution of task between agents, whether they have failed to follow policy, and then whether an operation should be escalated based on conflicts. And then all this is built on resource leasing. That is stage 1 and 2. Then we have starvation prevention by following decision layer. Starvation is prevented, and then by also following stage 4, scheduling and queuing, starvation is also prevented. And then we have conflict policy. So by following stage 4, agents the system ensures there is no conflict between agents when they are competing for task allocation and resources. And then we have capacity planning. So it is in section 6, you determine capacity, whether the agent are capable of handling the operation or not. And then all these ensure smarter task routing, balanced workload, control resource use, and reliable execution, reliable output, and completed task. So in chapter 4, in summary, these are the core ideas that we have there. Assign task should be assigned based on agent capability and based on task priority, following the rules that we have discussed. Then protect scarce resources. So resources should be protected, okay, by implementing rate limiting, implementing, the number of requests per time, or the number of, queue per time. And then 3, escalate high risk work. So when the task is very, very risky for agent, even specialist agents to handle, then there should be human in the loop that the task will be routed to be implemented. So this is what we discussed in chapter 4. If you need more in-depth information, please kindly get a book on Amazon. It is called Multi-Agent System or Multi-Agent Orchestration Pattern for Enterprise Scale System, where we discuss this architecture in detail and code guide for you to implement them as an agentic system engineer, AI engineer, site reliability engineer, or as an integration engineer. Uh, it is very, very, very loaded, guys, and I have dropped the link below. Thank you for listening. Please kindly like and subscribe to this audio so you get more information from us whenever we upload a video. Thank you.